Right now, as you're watching this, there's this incredible high-stakes balancing act happening inside your body. It's a core principle of chemistry, and honestly, it's what's keeping you alive from one moment to the next. So let's dive into this hidden world of chemical equilibrium.
I mean, just think about that for a second. Your entire well-being, your life, it's all tied to this ridiculously narrow range. If your blood's pH goes just a tiny bit lower than 7.35 or a little bit higher than 7.45, you're in life-threatening trouble. This isn't just some textbook concept, it's a critical biological reality for every single one of us.
So, that's the big mystery, right? How on earth does our body pull off this constant, super precise chemical tune-up? Well, the answer is this powerful idea that governs reactions everywhere, from inside our own cells to the biggest industrial factories on the planet.
And the hero of our story today is chemical equilibrium. Now, it's not about reactions just stopping. It's about them reaching this perfect dynamic balance. To really get it, let's just imagine a simple hypothetical reaction.
Okay, so picture a sealed box. We pop in 12 molecules of one ingredient, our first reactant, and 12 of another. Right at this moment, T0, there are no products at all. The reaction hasn't kicked off yet. We've just got our starting lineup ready to go. All right, now we let the reaction do its thing. A lot of people think that all 12 of those reactants would just get used up and turn into products, but that's not actually what happens. Instead, the whole system settles into this new state of balance. See? We've still got 2 molecules of each reactant left over. The reaction didn't just run to 100% and stop, it found its sweet spot, its equilibrium. And that little example, it perfectly sets up the formal definition. See, equilibrium is a two-way street. You've got reactants turning into products, but at the very same time, products are turning right back into reactants. The key thing, the whole point, is that the speed of those two reactions is exactly the same. So the levels look like they're frozen, but underneath the surface, it's total balanced chaos. It's dynamic, not static. So how does a reaction know where that balance point is? Well, every reversible reaction has a kind of rule book, a specific target value it is always trying to hit. In chemistry, we call this the equilibrium constant, or just K.
For that simple reaction we just walked through, the value of K is 25. That number is the specific ratio of products to reactants that this system is programmed to achieve. It's like its destiny, you know? It's a fixed set point. And this is what makes K so powerful. You can mess with the system all you want. You can dump in more reactants or you can scoop out some of the products, but the system will always fight back. The reaction is just going to relentlessly shift one way or the other until that ratio gets right back to its target value, K.
Okay, so if K is the destination, how do we know where we are on the journey? You need a GPS, right? Well, for that, chemists have another tool, one that gives us a snapshot of the reaction in real time. We call this the reaction quotient, or Q.
So Q is calculated the exact same way as K. It's just that ratio of products to reactants. But here's the huge difference. You can calculate Q at any point in the reaction, not just at the very end. It tells you the state of the system right now. It's a snapshot.
This comparison really just nails it. K is the fixed destination. That's the target your reaction is desperately trying to get to. Q is your GPS telling you your current coordinates. And when you compare your current location, Q, to your final destination, K, well, then you know exactly which way you need to go. And this, right here, is where it all comes together. This is the aha moment. By simply comparing these two numbers, Q and K, chemists basically get a superpower, the ability to predict the future, or at least the future of a chemical reaction.
And the logic is actually beautifully simple. If your snapshot value, Q, is less than your target, K, it just means you've got too many reactants hanging around, so the reaction has to shift to the right to use them up and make more products. If your Q is bigger than K, you've got too many products. The reaction has to shift to the left to get rid of them. And if Q equals K, perfect. You're there. You're at equilibrium, and the system is happy.
So let's look at a real-world example, making ammonia. Imagine a chemist takes a snapshot and calculates Q to be, wow, 12.5 million. But we know the target for this reaction, K, is only about 0.06. Since Q is just astronomically larger than K, it's obvious the system has way too much ammonia product. So the prediction is clear. The reaction will shift to the left to break down all that extra ammonia. Okay, so we've got our tools, K, the destination, and Q, the snapshot. Now we can finally go back to our original question and see why this matters so much, from our own blood to the entire world.
Remember that razor-thin pH range, 7.35 to 7.45? Well, the balance of carbonic acid in our bloodstream that maintains that pH, it's all governed by these exact principles of equilibrium. So get this, when a patient has low blood pH, a condition called acidosis, it's because there's too much carbonic acid. The system is out of balance. So what does a doctor do? They can give the patient bicarbonate through an IV. Now, bicarbonate is a product in this reaction, so by adding it, they instantly make the Q value shoot up way higher than the K value. And what did we just learn happens when Q is bigger than K? The reaction has no choice but to shift left, which consumes the excess acid and brings the blood's pH right back into that life-sustaining range. It's a life-saving procedure, all based on the simple, powerful logic of Q and K.
And this isn't just about medicine, not by a long shot. The Haber process, the reaction that makes ammonia for the fertilizers that feed billions of people, that's just a constant, clever game of manipulating equilibrium to get the most product. The same is true for making countless other chemicals we depend on every single day. Understanding Q and K is absolutely fundamental to our modern world. So from the fizz in your drink, to the air that we breathe, to the very blood running through your veins, all these chemical systems are constantly trying to find their balance. It's this invisible dance, all governed by the simple rules of Q and K, that makes our world and our lives even possible. Now that you know about this unseen balance, what are you going to see differently?